Hello there and welcome to A2 Maths from Specimen paper 2, and here we're looking at a rates of change question and then a logs question afterwards. So bacteria culture has area P in millimeters squared at time t hours after the culture was placed onto a circular dish. A scientist states that at time t hours the rate of increase of the area of the culture can be modelled by being proportional to the area of the culture. So the area of increase is proportional to the current area. Part A is show that the scientist's model for P leads to the equation P equals AE to the KT, where A and K are constants. So what we need to do then is to set up a differential equation to start with. So the rate of change of the area is proportional to the current area. So that's what we're looking for here. We're looking for dA by dt equals A, so Ka. So the rate of change, that's what dA by dt is, and proportional to, that's why the K letter is there, and A, that's the letter that's representing the current area. So what we now need to do is we now need to solve this as a differential equation. And remember, the way we do that is we group all the A's and the dA's on one side and all the T's and the dT's on the other side. We haven't got any T's, but we'll just put them on the right hand side. So we'll divide by A onto the left hand side and we'll multiply by dt onto the right hand side. And then we integrate both sides. So there we are. Now we've got an integral on both sides of the equation here, and we now need to solve it. So integral of 1 over a, that's ln a, and that's going to equal kt plus c. Plus c, remember, only needs to go on one side of the integrals here, because you can always group them together and make a new value of c. But anyway, here is our value for c on the right hand side. Now we need to rearrange this. So how do we undo the ln? Well, we take an exponential. So it's going to be e to the power of kt plus c. Okay, so it's nearly similar to what we've got it looking like here. I've used the letter A rather than the letter P. Let me just get rid of that now. P equals, and it's going to be e to the kt, and now we're going to break this part up here, the plus on the power there, by using the law of indices. And when we use the law of indices here, we multiply by e to the c. Remember that when you multiply two indices with the same base, you add the powers. We've kind of done that rule in reverse. Now what we're going to do now is we're going to set little a equal to e to the power of c. We can do this because c, remember, is just a number, e is just a number to the power of a number is just another number. We'll call that number a. So it's p equals a e to the kt. So there we are. That's our answer to part A. Moving on to part B, remember from part A it was P equals AE to the KT. The scientist measures the values of P at regular intervals during the first 24 hours after the culture was placed onto the dish. She plots the graph of ln P against T and finds that the points on the graphs lie close to the straight line with gradients 0.14 and a vertical intercept of 3.95. Estimate to two significant figures the value of A and the value of T. So what I'm going to do now is I'm just going to do a little bit of rearranging here. I think the first thing I'll do is I need to have a graph that's in terms of ln P and T. So I'm going to now ln both sides. So it's going to be ln P equals ln A e to the kt. So how do I now split up what I've got on the right? Well, when I multiply two logs inside the brackets, I can use a rule of logs that will split them up by having an addition between those two ln values. So now what I've got is I can simplify this back term here, ln of e, that will cancel each other out, so it's kt plus ln a. So now effectively what I've got here is I've got something similar to y equals mx plus c. Y is represented by ln p, t is represented by x, k is the gradient m, and I've been told in the question that the gradient is 0.14, so k must be 0.14, and the y-intercept, which is c is 3.95, but in my equation I've got c as ln a, so ln of a is equal to 3.95. So how do I work out what a is? Well, I now need to do e to the 3.95, and e, so let's grab my calculator, e to the power of 3.95 gives us 51 to two significant figures, 52 to two significant figures in this case. So 52 as the answer for A, and 0.14 as the value for K. So there we are. Let's now rewrite out this equation. We had P equals A, which was 52, e to the power of 0.14t. So that's our equation. It follows on by saying part C, hence show that the model for P can be written as P equals A times B to the power of T, stating to three significant figures the value of the constant B. So what we need to do is the A value will stay as the value 52, but what we now need to change this into is a B value to the power of t. Now what I'm going to do in the first equation is I'm going to rewrite this as 52 times by e to the power of 0.14 to the power of t. Now remember, when you've got a power of a power, you multiply the two power values together. Well, in this case, I'm doing the reverse of that rule. So I've split up the 0.14t into 0.14 as the power of e, and then to the power of t again. So I've got a triple power here, e to the power of 0.14 to the power of t, which will then, if we look at what we've got in both the models here, b is going to be equal to e to the power of 0.14. So grab your calculator and work out what e to the power of 0.14 is going to be. That's going to be 1.15027 ... So there are to three significant figures, so that's going to be 1.15. So there we are, that's the answer to part C. B is equal to 1.15. And now answering the next little subparts of the question with reference to this model. D part I is interpret the value of constant K. Well, if you remember what the model looks like, it looks like 52 times 1.15 to the power of t. So when t is equal to 0, p is equal to 52. So it's effectively the starting area of the culture. D part I, with reference to the model, finds the interpret the value of the constant b. 1.15 means that the area increases by 15% each minute, I think it was. Let's just go back a few slides just to see what the time measurement is. T is in hours. Whoops, I got that wrong. So each hour. And part E states the long-run limitation of the model for P. Well, if it's just going to increase by 15% each hour, eventually it's going to run out of room on the Petri dish. So it will run out of room on the Petri dish. I assume it's on a Petri dish. I'm not too sciencey myself. So there we are. That's the answer to question 7 then. A really interesting contextualised question that has multiple topics within A-level maths all put together into one really super interesting question there. 12 marks for that question, so you do deserve a lot of marks if you've managed to combine all of those topics together there. 7 marks for that question. That was question 7, 12 marks for that. Let's move on to question 8.